With Doubtnut, get instant video solutions to all your maths, physics, chemistry, and biology doubts. Just click the image of the question, crop the question, and get instant video solution. Download Doubtnut app today.
Hello everyone, so our question is, in an experiment of photoelectric effect, the stopping potential is measured for the monochromatic light beam corresponding to different wavelength. The data collected are as follows. The wavelength in nanometers is 350, 400, 450, 500, 550 and corresponding stopping potential is in volts as 1.451 and 0.66, 0.38 and 0.16. We have to plot the stopping potential against inverse of wavelength on the graph paper, and we have to find the Planck's constant, the work function of the emitter, and the threshold wavelength. Okay, now we know the relation between the stopping potential and the maximum kinetic energy of the photoelectrons is given as E times V naught will be equals to Hc by lambda minus phi. Correct? Where V naught is the stopping potential, phi is the work function. Okay, now we have to plot the graph between the stopping potential and inverse of the wavelength. So let us suppose that our stopping potential is y and our inverse of the wavelength is x. Okay, so from the equation what we see is E times y is equals to Hcx minus phi. Correct? Or what we can say is y is equals to Hc upon E times x minus phi upon E. Correct? Now relating it to the equation or comparing it with the equation of y is equals to mx plus c, what we see that the slope m is Hc upon E and the constant c is minus phi upon E. Correct? Now plotting the curve between the x-axis and y-axis, let us suppose this is our y-axis, this is our x-axis. Okay, this is y-axis and this is x-axis. On the x-axis it is 1 by lambda, correct, towards 1 by lambda, and on the y-axis it is the stopping potential V naught. Okay, now we can see that the intercept on the y-axis is minus phi, so the graph will look like this. Correct? And this distance is how much? This distance is phi upon E. Okay, and the slope over here, that tan theta will be equals to how much? Hc upon E. Correct? So the graph versus the stopping potential and the inverse of the wavelength will be this. Okay, now further going on the question that we have to find the Planck's constant. Okay, now from the given data we can see when the wavelength is 350, the stopping potential is how much? 1.45, and when the wavelength is 400 nanometers, the stopping potential is 1. Correct? So using that given data, what we say is at lambda is equals to 350 nanometers, our stopping potential is how much? 1.45 volts. Correct? And at wavelength of 400 nanometers, our stopping potential is 1 volt. Okay, now using the relation of stopping potential with maximum kinetic energy Hc by lambda minus phi, what we can say from here that 1.45 electron volts will be equals to Hc upon lambda is how much? 350 nanometers, or 350 into 10 to the power minus 9 meters minus phi. Let us suppose this is equation number 1, and the second equation will be 1 electron volt will be equals to Hc upon 400 into 10 to the power minus 9 minus phi will be equation number 2. Now subtracting equation number 1 and equation number 2, what we get is 0.45 electron volts will be equals to 1 upon 350 minus 1 upon 400, taking Hc as common, Hc upon 10 to the power minus 9. Okay, so substituting the value of C, what we get is 0.45 electron volts will be equals to 400 minus 350 divided by 400 into 350, correct, into H into C is 3 into 10 raised power 8 divided by 10 raised power minus 9. Okay, on solving this we will get the value of Planck's constant H, and the Planck's constant H will come out as 4.2 into 10 raised power minus 15 electron volt second. Okay, so this is our Planck's constant. Now in the second part we have been asked that what will be the work function of the emitter. Okay, so we will use one of the data from the above. So for the work function, Hc by lambda minus phi will be equals to E times V naught from the relation of stopping potential and the maximum kinetic energy, correct. Now the Hc in the electron volts nanometer is given as 1240 electron volt nanometer divided by the lambda is 350 nanometers minus phi will be equals to the stopping potential corresponding to 350 nanometer wavelength is 1.45 volt, so it will be 1.45 electron volts. Okay, so from here we can calculate the work function phi, and the work function phi will come out as 2.15 electron volts. Okay, now in the third part we have to find the threshold wavelength. Okay, so we know that the work function is Hc upon the threshold wavelength. So from here we can calculate the threshold wavelength will come out as Hc upon phi. Now Hc is how much? 1240 electron volts nanometers divided by the work function we have calculated, that is 2.15 electron volts, correct. So from here we can calculate the threshold wavelength. It will come as 576.8 nanometers. Okay, so our threshold wavelength come out as 576.8 nanometers. Okay, so this is all our answers. Thank you.
For class 6 to 12, IIT JEE and NEET level. Trusted by more than 5 crore students. Download Doubtnut app today.